Okay, today we're looking at 1.2, and you'll notice this is solidify understanding. So we're starting to learn a little bit more about this new type of function, which if you look at this module is called a quadratic. So the first question it asks here is how many squares will it take to create this I logo, right, size 100? And the answer is 502 squares. So this is one of those things that you probably do not want to keep counting all the way to size 100. So you may have noticed that this first one has 7, this has 12, 17, 22. So you'll notice that each time we are adding 5 more. There's a few different ways you could have seen that in the picture. I saw it as kind of like adding the 4 on the outside, and then 1 more in the middle, so 4 on the outside, and then 1 more in the middle. Okay, so let's talk about how we got that 502. We probably noticed that we started with 7, and we're adding 5 each time. But remember that, when we got to size 2, we only added 5 once. When we got to size 3, we added 5 twice. So remember our formula has that like x minus 1, so we're going to do 100 minus 1. So we're really doing 7 plus 5 times 99. And that's where we get our 502 squares. This is 7 plus 495, which equals 502. Okay, so now we want to develop a mathematical model. Models can come in many ways. Remember, you can have equations, you could have a table, you could have a graph. In this case, I'm going to just write a formula similar to what I had up above. So I had f of x equals what I started with, 1 plus 5 times x minus 1. And if you wanted to simplify that, this does equal 2 plus 5x. And those are equivalent. I know some people like the recursive equations. So if you want to try something like that, you'd have like f of 1 equals 7. And f of x equals f of x minus 1 plus 5. You could have done something like a table, right? So a table would have looked something like this. You'd have like the size, and then the number of squares, they said actually, rather than blocks this time. So squares. So you'd have 1, 7, 2, 12, 3, 17, 4, 22, maybe get a little ambitious, you'd be like 5, 27, 6, 32, right? You could have even had something like a graph. Remember, if you're going to do your graph, make sure you label things. This is the size, which we had 1, 2, 3, 4, and then we'd had squares up here. And by the time we got to 4, we're all the way to 22, so maybe I'm going to count by 5, so like 5, 10, 15, 20, 25, and then you'd have to start plotting points like 1, 7, 2, 12, 3, 17, 4, 22. You would want them to be separate points, right? Because this is discrete. There's not like a size 2.5. And it should make a straight line if you set up your axes well. Okay. At this stage, I want you to pause, and I want you to go ahead and try to answer questions 3 through 5 before we come back together. Okay, as you're ready, let's go ahead and take a look at questions 3 through 5. So on question 3, it asks you to draw this block, and you want to find out how many blocks there were. So if we draw it over here on the right, I kind of numbered those just to keep me so I was aware of how wide it is, but it's going 4 down, right? It's going 12 over, goes 4 down, goes 4 in on both sides, right? Comes down 4, and then the bottom is a mimic of what you see on the top. So the eye looks something like that. And whether you counted it out or you came up kind of with some shortcut, here there should be 112 blocks. While this is not the only way to see it, one way you may choose to see it is if I break these up, you'll notice here you've got 1, 2, 3, 4, 5, 6, 7 blocks of 1 by 1s, right? I could do the same thing here, right? Break it up. I have 1, 2, 3, 4, 5, 6, 7 blocks of size 2 by 2, right? And this last one, you'd see, okay, 1, 2, 3, 4, 5, 6, 7. So you may see that there's 7 and then blocks for size 4 of 4 by 4s. Or you could say 7 times 4 squared, which in this case does equal that 112. Okay, so now let's come up with a model, right? Models can take many different formats. In this case, we kind of already have an explicit equation. We said, hey, we're doing 7 times, that x squared. Or you could have x times x, right? This 7 times x, that's the equivalent. Not the only way to see it. You could also see it as a bigger square with getting some taken out of it, right? So just be aware, like, there's another formula I came up with that was like 3x squared minus 2x squared. Those are actually all equivalent. You could also come up with like a table, right? So a table, you may have something more like this, so size and then blocks. So 1, 2, 3, 4, 5, let's say. So we get 7, 28, 63, 112. And if I go one further, I actually get up to 175. Here, you may notice a little pattern. If we start adding, I get 21, and then I get 35, and then I'm getting 49, and I'm getting 63. Those are all multiples of 7, which is kind of interesting. If we look at that second difference, remember how we said that's going to kind of be a key thing here? Notice each time we're adding 14. Okay. Did anyone try a graph? If you tried a graph, let's see if we can do one here. Oops. So we've got squares or blocks, whatever we're calling it. We're going to call it blocks. This is the size. So let's just do the first, like 1, 2, 3, 4. I'll do 5. So I have to go all the way up to 200. So maybe I'm going to count by 50. So 50, 100, 150, 200. Remember, you got to keep that scale equal. So to get up to 200, I just chose to go by 50s. You could choose by something else. That's a nice, easy way to count. So 1's going to be pretty close down here. 2's going to be about halfway. 3 is going to be just above that 50 mark to be 63. 112. And then 175. So you'll notice you're starting to get kind of this curve pattern, but be aware, not exponential here, but it does have some curve pattern. And I'll just throw this out there. I do not expect you to have written this down, but if you wanted to do a recursive, you actually would have f of 1 equals 7, and f of x equals f of x minus 1 plus 7 times 2n minus 1. 2x, sorry, minus 1. You could have 14x minus 7 if you prefer. So that's 4 different ways we could have seen it, right? Any of those ways are possible ways you could have done it. Okay, so in what ways are they similar and what ways are they different? So let's think about it. So we got the first and we got the second. I always like to think about it as like a little Venn diagram when I'm thinking about things similar or different. So the first, oops, that was a bad circle, my bad. There we go. And the second. So, and the first one, this one is a linear, right? The second one is something different that we don't know. It's the new one, right? And we're going to start calling that a quadratic. So this one has a constant, right, rate of change. Whereas this one, the quadratic, has a common like second difference, but not first like this one does. Common first difference, meaning you have to do it twice to see that common one. What else? So if we looked at the graph, the linear one is a line, right? Whereas the second one is a curve. Be aware right now we're only seeing half of it. We're going to call that curve eventually a parabola, and it's actually going to make a U shape. In your equation, you do get like an x squared here, whereas this one just has like an x, right? Something that they both have a starting point, right? They both increase, but I'm going to put a little star there because right now we're only seeing half of it, right? So the parabola actually does something interesting on the left side that we'll see as time goes on. Yeah, so that's some of the things that we see. If you've got other ideas, go ahead and add them in there.